research project I started working on. It's simulating EEG signals and EMG signals and how we can change and how they do change based off parameters that we can change. So what we have here is a graph of a normal EEG signal that was simulated, and we have our amplitude on the Y and timing variables on the X. And as you can see, basically what we're looking at is if we do a point here, we can actually look at, we have obviously a point of our timing is 3.7, and we have our amplitude is 39.5. And then if we go down below, let's say we're right here, it's 3.29, so about three seconds, 3.29 seconds, and then we have our negative, it's a negative amplitude, we have negative 37. So, and then what we did is we actually, I broke it down among the, I did a little research as to how the EEG signal is created by looking at the different waves. So what we have is we have our high amplitude signal, which is one of the waves that create it, which I believe that wave is actually our delta wave. So we started with our delta. Here's the waves right here. What we do is we have our defining parameters. We have our sample frequency. So our frequency is 500 hertz. Our timing vector from 0 to 10 seconds. And then we have the number of samples that we're taking, which is just the length at the certain time, the time interval, right? So what we did here is we're actually looking at and then we have our sine waves, and how a EEG signal is created is with these sine waves. So we have our high amplitude, we have our medium amplitude, we have our prominent amplitude, which is our normal, and then we have our low amplitude. Our prominent amplitude is our standard wave, so our alpha wave here, which is our these are all sinusoidal waves that are created. Our alpha wave is actually at our ideal, right? So our ideal normal wave is our alpha wave. And what I mean by that is this is our relaxed, this wave is when we're relaxed and we're idle. Then we have our delta wave, which is deep sleep, when we are unconscious, we're really not thinking. There's no real brain activity, nothing really major, so it's more wide awake. There's more spaced out. Then you have our theta wave, which is our drowsiness, which is going to be when we're kind of sort of tired or we've exerted ourselves. And then we have our alertness, which is going to be very, very close together. And we can see that when we go to these waves here. So this high amplitude wave, like I said, you see the spacing between it. This means that we're looking at our different spacing. So you look at, okay, this is at 4.8, the next one is at 5.1, right? So longer stretches of time for activity, for changing in amplitude. So we have longer changes, longer time intervals for amplitude changing. Then we have our medium amplitude, which is drowsiness, a little bit tighter, as you can see. But if we go and we look at this, we still have, it's a little bit tighter, right? So we're looking at, okay, 1.3 to 1.7. So now we're looking at from the top of this one And we can go down, 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 down. And if we go down to the bottom is 1.7. So these are happening, the amplitude changing when we're drowsy is pretty quick. And then we have our another signal, which is normal. This means idle and relaxed state. Obviously, you can see it's very condensed together. It's very rapid. We're having a lot of changing amplitudes in this. And then we have our low amplitude, which means we have alertness. Alertness means that everything's condensed together. And that would make more sense. It would be more frequent. The amplitude would be changing rapidly. Then what we have is we have our normal EEG signal, and then we have a simulated normal EEG signal. The normal EEG signal is literally going to be, we're going to take all of these EEG signals together, and we're going to combine them. And then what we're going to do is we're going to add this Gaussian noise, which basically is a standard, it's basically a standard noise level. And when an EEG reads brain signals, it actually adds, the machine is actually adding this noise, this Gaussian, this random Gaussian noise. So we're adding this random Gaussian noise as to simulate a real EEG and how it would react. The actual EEG signal is just those waves, the normal, so that other graph, which is this one here, the normal EEG signal, is just all of those waves compressed together. So with all of those waves compressed together without any noise, this is what we get. And as we can see, that would make sense. So in a normal sense, this is what we should see without noise. And the little areas here are caused by your low amplitude. You have your low amplitude and your idle, your prominent amplitude, and also your medium amplitude, all creating these really close-knit areas. And then you have obviously your other amplitudes, which are creating these outer, upper, and lower areas are actually created. So prominent and low amplitude create the middle, and your medium and high are creating these outer stretching parts. And then if we look, we add this noise. When we add the noise, you can start to see that the noise is a factor. And now it kind of makes these things a little bit harder to read. And we can zoom in on this. So we can zoom in on it. We can actually zoom out. But if we zoom in on areas, you can see that there is noise on these signals. Unlike here, where if we zoom in on it, it's clean. We can see the actual changing among these waves that we're combining. So that is essentially what I did in creating this and how I went about looking and simulating an EEG signal. And there was other things that we could do. I actually have down here where I actually was like, okay, let's actually go ahead and do a spectral density of the simulated EEG. So if I do a spectral density of the simulated EEG, which kind of shows us what we're doing here, we can actually go ahead and run this. And what we have is we have a PSD. Our PSD is going to be something like so. This is our spectral density of simulated EMG, so our PSD. And our PSD is showing the power slash frequency over the frequency that we're getting. So we actually have simulated EEG. We have our simulated EEG, and we're looking at our power and frequency. And as you can see, when we first start off, there's a lot more power and frequency. And then as time goes on, it starts to drop down. Our power over frequency drops down and becomes low and negative across as we go past a certain frequency. So if we look right here, that frequency that we start to hit, so around 22 hertz, 23 hertz, we actually, for our frequency, we start to, the power per frequency starts to go negative. So that's just something that we have there. So that's something we have there. And what we want to do is then we did our EMG, and our EMG is something that we're looking at a regular EMG signal and how it would work and affect and be affected. So what we have is we have a so what we have is we have that um and we're looking at, again, we have our parameters, our frequency and time, and the number of samples. Then what we're looking at is we're looking at the number of motor units. And these number of motor units actually are, so each muscle has a number of motor units in there. So when you contract or decontract your muscle, it has a specific motor unit or a specific number of motor units. So for our 250, this is actually our voice box. And then we have our base frequency, we have a peak frequency, we have an activation, which is it's basically a threshold, if you will, or a number that is used, or a percent that is used to activate the motor units. And we can see right here, 0.2 is low threshold units, and 100% is all, obviously. So we're using 60% activation. We have our threshold, which is going to sort the random 1 to the number of motor units, and we're going to square that upon by 0.3. Then we are going to we have our recruited. So what ends up happening is as these motor units get activated, we actually, there's new motor units that are recruited, and they're recruited based off this threshold. So based off the threshold, we're actually recruiting more and more motor units that are getting activated. And then as you can see right here, we have recruited the recruited um, motor units, if you will. So the recruited number of motor units. Then we have dynamic contraction, which we can add. I didn't add it here, but you can add a dynamic contraction. We have our motor unit, so our MUAP, which is basically our motor unit activation process duration. We can actually have our duration, the length, so this is biphasic waveform, so this is going to create a biphasic waveform. then we have our tau, and we have our x, and we actually will have our base for our MUAPs. This is all about calculation. This was me just looking up how these things are calculated and how MUAP is actually calculated. What do you need? I did a lot of research on that. Obviously, in calculation, we have a tau, we have an x, which is more for symmetric timing, and your timing axis, you have your basic waveform that you need, and then you have your baseline for your MUAP. And then you are going to prepare your motor units, vary amplitude and slight shape of them. So what we're looking at is we're looking at the length. So these also have a shape to them. So these motor units have a shape, and that would make sense because of the muscle. Every muscle has a different shape. And we're also going to consider the amplitude, which is the number of motor units that we're looking at. You can add parameters for direction slash fatigue. So we can add a fatigue or direction if we wanted to. You can also define agnostic or antagonist recruitment depending. And then we have a for loop that's going to go through, and we're going to have our amplitude scaling factor. We can add activation to that. You also have a slight width variation, which is for shape, and more calculations for the MAPUs, all right here. This is all the calculations. Then we can create a subset for push and pull, agnostic and antagonist. So we can actually create these subsets for pushing and pulling of the muscle. We also have fatigue of the muscle we can add. And then we're going to end that. We use gamma ISI generator, which gamma ISI generator is one way of calculating the, or one way of simulating the muscle, or simulating EMG signals, which is the electromyography type signal. And what we have is we have a total, we first will create a total simulation time. We actually have case shape, meaning we have the shape parameter, so a gamma shape parameter, lower equals stress. So if let's say your CD is 0.5, you're looking at if it's lower, then there's stress being put on that muscle. Then you have an optional absolute reference in seconds. You have spike gamma, which is gamma spike train. So what we do is we have these spike trains that we create. Then we have another for loop going through, and we're looking at the recruitment, and we're also looking at the generating of the spike times for the gamma spike train. We also can do direction based if we wanted to. You can add direction. We also have dynamic contraction. If we wanted to add dynamic contraction, we could. We are going to draw gamma ISI. You'll see what this is in a minute once we run this. And then we're going to enforce absolute value reference. And these are all spike trains. Then we convert the spike times to binary vectors. So we're actually going to take those spike times that we have. So these spikes are kind of relating, like if your muscle's moving. So, right, we have these spikes in our muscle or signals being sent to our muscle, and that's what these spike times are. So now they're going to be converted to binary vectors. And then we're going to look at the ones that are not recruited yet. And then we could also do Bernoulli. We can also use Bernoulli per sample approximation of Poisson. And we actually can create spike trains doing that and add into Bernoulli as well. And we can convolve spikes with MUAPs, and the sum, but we did gamma ISI, which is more of what they do or what the EMG machines actually use or calculations actually use. And then we can actually we're going to clean up the EMG signal, and we're going to add a baseline noise, obviously, from the machine, kind of relating to the machine. For noise that's coming from the machine, we're actually going to add, again, you can add mains hum, which is optional, an optional second harmonic if you really wanted to. We can generate random white noise to represent interference patterns in the MUAP. We're going to then do a bandpass filter on the raw signal. We're going to remove low frequency motion, and we're going to remove high frequency noise. We use the Butterworth filter, which is a bandpass Butterworth filter. Then we are going to filter. You can add 60 hertz again for main hums if you wanted to. Simulation, then we're going to simulate our muscle contraction. This is rectification and smoothing. We have our low pass filter to simulate the filtering effect of tissue. So this is because there's tissue around the muscle, we're looking at that effect on the muscle with the tissue now. And then we're going to apply the filter to the rectified signal. We're going to scale the signal to a more realistic amplitude range, and then we're going to plot. So we're actually going to plot the raw bandpass filter. We're going to be plotting the rectified EMG signal, and we're going to plot the simulated EMG signal. There's other things we can do, which is plot the gamma spikes, which is a raster plot. We can also plot FFT and plot EMG frequency and a spectrogram. So let's go and run this. So the first thing that I want to show is this is the raw bandpass filter. It's not readable. It's very hard to understand what's going on. We see that there's amplitude, but we also see that there's time. It's very condensed together. Now, what we're going to do is we're taking this raw bandpass and we're going to rectify the normal EMG signal. So we're going to rectify it and set it into a range. Still, the signal is kind of all noisy and very hard to understand. But then what we do is we take that rectified signal and we smooth it out, and then we can simulate a nice normal EMG signal. And as you can see, at first, amplitude starts low and builds up, and then it continues to then stay within the range of about 3,500 microvolts. So about 3,500 microvolts to, I think the lowest that we end up actually going is like 2,000 microvolts across the time span that we started with. So at 0, it builds up, there's no muscle contraction, and then all of a sudden we're starting to read that there is muscle contractions and movements, and there is movement across the tissue. And as you can see, we're looking at these amplitudes changing. And what we could do is we can also do a plot, so we can actually look at this. So we're going to take this out here, and you're going to see so, and then we have this, and let's open up, let's do all of the, no, we won't do FFT. let's do, and we won't really show the frequency. You can play around with that if you wanted to. But this one's kind of cool. This is actually a spectrogram showing you some really cool, interesting things as well. And like I said, understanding these things took me some time, so it does take time to actually understand what we are looking at. So what we have here, this is our spike raster, this is our gamma ISI. These, it's hard to see, but if we zoom in, you can see these lines, these little dots, okay? These little dots are actually motor units. So we have the number of motor units, and we're looking at the number of motor units, and we're looking at how many times these motor units are actually triggered. So you can see these little dots. These little dots are actually how many times the motor unit is actually triggered. So let's say we're right here. Okay, that's motor unit 34. Motor unit 34 was triggered 4.1 at 4.1, right? So what we're looking at is we're looking at these trigger points of the motor units. And then what we can do is we can look at the time frequency EMG, which is the spectrogram. We're looking at the frequency over time, and we're looking at the coloration here. So the colorations here, we're looking at if the coloration here is the representing the time frequency activity within that muscle that we're focusing on. And you can see that we have these blues, then we go to the lighter greens, then we go blue again, and the darker blues, and then you can see down here that at these low frequency points we have these oranges, these yellows. So that's another thing that I ended up doing and displaying. So that kind of covers what we did for that kind of covers what we did for the EMG signal. And like I said, I did a lot of research on how these signals worked, what they entailed, and what they were and how they functioned. There was a lot of looking at the calculations, especially when it came to EMG signal, especially when it came to like figuring out how the EMG signal is actually created, what parameters they actually use, and you can actually look this up. This all came from online. I looked at I just kind of searched up on Google. I searched up from articles, and I've also searched up from GitHub on some of these things and figured out how to simulate EEG and EMG signals.